welcome back everyone. This is part B to the simulating mass spring damper second order systems. Just as a quick rerun, if you remember, because I'm not sure if you've continued straight from the first video, we established static sensitivity, we established the damping, we established the spring rate, the velocity, position. We even plotted to the workspace so we could extract this great data that we're getting. We did a scope. We looked at having scopes on the top of each other, so for two plots within one. We've applied a subtraction, and then we ran it over 40 seconds, giving us the output. Now, if you remember, the C, K, and M were all established by variables. 2 seconds. Let me just call up my MATLAB. Now, if you remember, these were the variables. So we set C as 0.5, we set K as 1, and we set the mass as 2 kilos. I'm just going to delete that because that's the last set of data from the Simulink model. What I'm going to do now is I'm going to just move on to a different one. We're going to keep bouncing backwards and forwards with Simulink because I'm not saying Simulink is poor, because it's far from it. It's incredibly powerful. I just want you to get a feel for different tools that are there and how useful they can be. So we're going to stay with these variables, and we're going to replot the same system into something else. I mean, into Simscape in this case. So let me just find my model. There we go. So let's get back onto here. Now, for argument's sake, I tell you what we're going to do. We're going to turn this into its own block. Let's compare the two. Love comparison. Love it. So what we're going to do is I am going to sever this, and I'm going to... Right, now you need to follow me on this. Left click, drag, highlight all of these blocks here. Then I'm going to right click, scroll down, and you'll see create subsystem from selection. This is a great tool because if you end up with a model which has, I don't know, 40, 50,000 different configurable things, like for example in my engine, I had a 150 layer system, and it would allow me to simply navigate through the mathematics of the actual engine. And it was a theory that I'd had when I first started thinking, if we take the simplest of equations and gradually build up these equations and have subsections, this will be a visual representation of the engine in its functionality, but in mathematical format, stroke computer-aided design. Then I could use the CAD model, but then apply these theories all the way through. The methodology worked really well, and in fact, it's what we're going to keep using. So I'm going to left click. What you'll see now is everything seems to have vanished. You get this lovely, this is new by the way. I know I keep going on about stuff that's new, but that's new. I love that. That's so cool. This is a little bit of a preview of what is sitting under the shell, under the mask as they say. So what I'm going to do is just double click in, and what we've got is our first model, but in its own organized format. We can have signals coming in and out at the same time. It's great. I really do like this. So if you'll notice up here now, it's been actually denoted as a subsystem to the mass spring damper model. So I'm going to left click, bring it back out. Right, so I'm going to put that into position. And what we're going to do now is we're going to model the same system in Simscape. It's just so... I mean, because at this point now, I am confident that you're aware of the equation, because we've talked about the equation. I'm confident of why we'd followed through with different ways. What I want you to be now starting to think about is what these other systems do, because the trouble is with a lot of systems nowadays is they will do it all for you, and sometimes, I mean, I'm just as guilty, sometimes you can walk away and go, that's amazing, and it's done so much, and you just ignore it. You know, you just go, that's my result, happy days. But if you know what's going on underneath the shell, if you know how the engine's functioning, lack of better words, this allows you then to really understand the scope of what you're working with, because then you can say, well, it's using a second derivative. It will have to be using a second derivative here. So let's not mess around anymore. So this is just me adapting the same model that we had. So if you didn't save it, I would recommend you go back to part A, rebuild it, save it, and then come back on. So I almost said I'll wait for you. So anyway, let's go to library browser. You'll see there I'm still in Sim to Workspace, which is the last block that we dropped in, if you remember. What I'm going to do is I'm going to now shrink my Simulink, and what you'll see here, I want to shrink these down so you're aware. Come all the way down when you see Simscape. Left click onto Simscape, and this is what it gives you. To be fair, when you first look at that, I looked at it, I mean, when I was a student and this was first coming out, I kind of looked and went, Sim, what? Doesn't make sense at all. Not sure. So, let's move in. To the left side, you've got your expansion, or expand the family, or is it the child? I always get myself mixed up with that. But anyway, expand it, and then within Simscape, we have these key elements. Electrical, by the way, you can even build a 7805, which is a voltage regulator. You can look at specific circuits that you're designing. I'm hoping, because the webinars allow me to open up to quite a large element of what these systems can do, I'm hoping that in time I'm going to introduce an electrical tutorial as well, and showing the overlap. The overlap's amazing. I love it. I absolutely love it. Anyway, let's get back to what we're talking about. Now for this, we're talking about, because the mass spring damper is such a fundamental thing that's been solved, we're actually going to use a foundation library. Within the foundation library, what this does is it kind of says, right, these are your fundamental system elements. So when you think of a spring, you think of the spring, you think of it's either compression or extension. You think it's going to have a wire thickness. You think it's going to have a wire thickness. You think it's going to be made of a certain material. But when you're solving these equations, you're in essence not considering these. You're considering these in a dynamic aspect. You're considering to tune. Once you've tuned what you're looking for, then you go back and you look to try and find your correct requirements for that spring or whatever it is that you're doing. And then you're obviously then restrained by the manufacturability of what it is that you're designing. So it's always something to keep in mind. So let's move on. From the fundamentals, I'm going to go to mechanical. Then I'm going to go to mechanisms. No, I'm not. I'm actually going to go to translational elements. You'll start to see things that you do recognize. You do terminologies that you recognize. So what we know is we're doing a mass spring damper example. So I'm going to drag in a mass, obviously. I'm going to drag in a spring. Don't worry about the rates. We're going to set these by variable. Boom. Stop saying that. And I'm going to drag and drop translational damper. So what we've got now is we have all zeta value, spring stiffness, all actually predefined within these blocks. This is why, for me, another reason why I love MATLAB so much, because they've looked at the reoccurring elements of something that you're building, and they've said, right, these things occur, we can put these into translational blocks. Now, if you look down here, this block that we made, we've done the same thing. All they've done here is they just made it that little bit more sexy. Now, when you have an open mask like this, you can go in and out. However, when you have predefined masks and there is code sitting underneath which is sensitive, this will stay restricted. So I cannot look underneath that. It's kind of like MATLAB saying, look, you know, you can use it, but don't dick around with it because it's our function. So we respect that. I mean, let's face it, they are some very well established company. Okay, so moving on. We got the spring, we got the mass, we got the spring, sorry, we got the mass, and we got the damper. We do need one last thing. We need a point of reference. We need to tell it exactly what that displacement's going to be. We need to tell it where it's actually going to be. What's the configuration for this? 2 seconds. Gotta love coffee. So, I'm going to bring in a mechanical translational reference. Now, those from electronics, you'll realise that that is technically a ground. But this refers to a reference point for this thing to operate around. If it doesn't have a reference point, it can't solve because it's just a free-flowing body through space, which is useless. So, what I want to do is I'm going to align these to actually suit. So, the top, the mass, notice this spot. This spot confirms that that is a point of where you actually tab into. So what I want to do is I'm going to spin that round. So select on mass, Control R, R. Right, and let's bring up my damper, and then bring in my spring. And what I'm going to do is I'm going to put this ground at a point of where it relates to. Now, if you think about how I'm drawing this, if we come back to the notes itself, think of this. There's our point of reference. Then we have the mass. So I'm actually drawing this as it should be. I mean, arguably, to make this even easier to translate, let's rotate that a little bit. This is off the cuff, by the way. I didn't intend to do this, but and then let's rotate that and rotate that. Then let's connect these two up, because we know that these are connected. They have a relation to each other. Reference goes to here, right? And if I bring the mass in, and I'll swing this round. Oh, a little bit too much. Swing it round, and what I'm going to do is I'm going to connect these up. And I know it's nerdy, but I don't care. Hell, if you think it's nerdy, turn this off. Now, if you look at how I've drawn it in the traditional method. I should point out, these notes, by the way, again, still John Calderbank's notes. Again, it's still extremely good, and I love them. Hence why I've still run with them, because I think that they're extremely good for in essence learning all about this. Right, let's get back to it. Let's zoom it in, and I just want to move that. Oh, well, I just want to move that. Oh, this is going really well, really well. I'm really pleased. There we go. So I'm just going to move that, and what I'm now going to do is just pull this down a bit. Right, now let's remind ourselves. Mass was M, damping was C, and spring stiffness was K. So let's get all that sorted first. So let's double click into mass. Was M. Spring was K. Oh. Damping was C. So now there's some things that we've not done yet. I need to slowly get you through this. A few things that you need to be aware of this type of function. So what I'll do is double click back in for a second. First thing that I know is we've got a deformation. We can presently define a deformation change. So I'm going to click onto deformation, and if you remember, we defined our first offset as y 0. Because we had it as 1 meter, if you remember. So right now the thing is how these things work is because all these ODEs have not ODEs integrations have now been collected into a new type of format, the system needs to know how the hell are you going to solve it. 2 seconds. Yeah, the system needs to know how you're going to solve it. So what we've actually got to do is we've got to say to it, we're going to use a solver. Now these solvers are really quite good. These are like a miniature version of the simulation solver itself, but by being able to, if I put a solver into this, I can tell the system to react in my specific way, if you will. So it's like a sub way of controlling this solution. Because if I go into here, for example, and then change that to just Euler, everything is dictated. But if I use a solver, it allows me to control just what I'm after. So let's just go back to the library. And if I minimize my mechanical and then come into Simscape, we have utilities. Love this software. So I'm going to drag and drop a solver configuration. Right, and then now, first thing, so I just want to attach this because I want to show you the magic. Just want to show you what happens. So I'm going to drag and drop, tab that in, and double click into solver. Now we have consistency tolerances. We can make this system be relative in its own tolerance. We can use local solver methods, backwards Euler methods, trapezoids, or whichever way we choose to do, whichever way we choose fit. We can even dedicate the amount of delayed memory for the budget in kilobytes. So we can spam the PC. I'm not saying spam your PC, but what I'm saying is that this solver allows us to really define how this system's going to move. It's murder, because I'm actually just recording my voice. I'm actually moving my hands like I'm talking to you. Anyway. For this, what we're going to do, I should point out as well, if you look on here, what we can do is we can actually pull the normal solvers and you can test your own solver in your own methodologies by using these techniques. I won't lie, I am no physicist. I just love the stuff that moves, and I'm going to trust the extremely famous solving methodologies. And I like to stay with MATLAB's auto methodology. They always the typical one it will always go for is the ODE45. Best way of running it. Anyway, so let's move forward. Click OK. Right, before we run, hit save, and then let's run it. It did nothing. Well, it did. Well, it did do something. This is similar to our Simscape method. Issue that we've got now is we've simulated it and it's no idea what exactly we're talking about. What we've got is this is our system method, if you will. Now, this was before we actually pulled a plot out. Now, normally in any sort of dynamic software, any sort of dynamic simulation software, what you're actually trying to do is you build the model and then you essentially probe to specific areas to give you any type of result that you're after. And what we've not done is we've not probed the area, which sounds really bad, but we've not established a probe onto any point yet. So what we're going to do is we're going to go back to the library. I'm going to go back to fundamental library. I'm going to go to mechanical. See how you have sources and sensors. Sensor. Ideal traditional motor sensor. Torque sensors. Ideal rotational sensors. Let's have a look what else we got. No, I'm just looking at what we got. I'm looking for one that will give me the motion. My main focus is the motion of this. So let's have a look. Ideal rational motion. Ideal traditional motion. Transitional motion. Now rotational motion, obviously angular velocities and so forth. But we're after ideal translational. Now with the translational, it just implies that it has a prismatic sort of behaviour to it. In other words, velocity, acceleration position. So what I'm going to do is I'm going to drag and drop this little beauty. Initial position. Let's call this Y0. I don't think it's going to like that. Didn't like that. I've had this problem before. So you look there, Y0. Just doesn't seem to like me using. Let's try Y0. Ah, I think I've actually just written yo. Anyway, moving on. So what I'm going to do is I'm going to use this as a probe. The R literally is pretty much saying, as it's reading in, what are we reading for? So I'll double click in just to show you. Now, this is talking about its initial position. We know that we'd set that to 1. And what we're after is actually the positional offset. When it comes to C, I actually don't want anything from that. But it needs to be attached. You'll notice that the output here, it needs to know what its reference point is relative to. Now, if you remember in our first simulation on Simulink, what we were relative to was 0. We were assuming our initial point, our ground point would be 0. So what we do is I'm going to right click and I'm just going to drag a copy of this and connect these two up. This now grounds it. Makes it bang on. In any of these types of simulations, there always possibility of crashing. So if you've not done, make sure you hit save. I'm going to do it myself. Let's hit run. Still not done anything yet. There's a few more things we need to do. So when this is in here, this has 3-dimensional matrices that's applied to it, regardless of its direction. What we need to do is we need to convert it from this into what they call the power stream. I don't know why they call it the power stream. It sounds dead cool, I won't lie. It sounds very Ghostbusters. Right, so I'm going to minimize here, and we're going to go to utilities again. Now, a good way of doing this, I know it sounds really silly, but because we're presently in the power stream and we've got all 3 coordinates being played, X, Y, and Z, what we need to do is we just want to isolate just one data type, in essence bringing it out for something that's Simulink to read. So if you look here, I've got power stream to Simulink converter. This was under in Simscape and it's in utilities. So what I'm going to do is drag and drop as we go further and further through these. By the way, I'm going to speed up on dragging some of these just because I want to presume that you've done some of this already. Just makes it easier. So where we have power stream to Simulink converter, let's drag and drop one in. Brilliant. So that's it. That is the magic. I'm going to just double click in. I want you to see this. Now, velocity, position. We're just comparing position. We can you compare velocity, it doesn't really matter. I'm going to double click in. Look at that. Output signal. What should we put it in as? Now the beauty is if a unit is not on there, which often you'll notice these things aren't on there, you just tap it in. So if it's degree, tap deg. And this allows you then to refine it even more, make your simulation so slick. It's squeaky, you know, it's very good. So I'm going to go output signal. I'm going to put it into meters, click apply, and then go. What I'm going to do now is connect you to you, and then run. I mean, I don't want to get too cocky. I don't want to get too mouthy, but you've got to admit that's pretty shit up. That is both outputs. That is Simscape versus Simulink. Output, the overshoot between each, identical. I'm just trying to really show you here that the solvers it uses is all still the same. The method for applying this is all still the same. but the simplification of building the model can often be easier when you're aware of how this function works and you're aware of how this works. Now this is just simply a single mass spring damper, but what if you were looking at something that was a bit more pliable? What if you were looking at something like a double mass spring damper? And the amount of students that have, or people, a lot of people have said to me, well, where would you ever see a double mass spring damper? A suspension. Now, the most interesting one I'd seen for a double mass spring damper is an earthquake detection. This is incredibly cool. Well, I don't mean what it's for. The lower earthquake detection will pick up noise. And if the lower one begins to oscillate, but if it oscillates so strong, the noise then transfers to the second one. This then causes the actual thing to really, really vibrate. This is where your Richter scale comes from. It comes from the second, because what it's actually done is the lower one, again, cancels out the noise, but the upper one will record true deflection of what's occurring. And it's just very, very impressive. Anyway, so we've taken a look. We're getting the same. It looks good. It's bang on. It's exactly what we were planning for. And we've now gone a little bit more deep, a lot more aggressively deep. It's a lot more impressive. It looks a lot better. So let's just put this into the same format as this. If you remember, drag, right click, create subsystem from selection. Where's that one coming from? Oh, that's coming from there. If you don't like it being there, you go, I didn't want that. I can just go, I didn't want that. Take it away. And then that's what you get. Again, one thing I didn't like there is let's go position in meters. Let's run it again. Oh, that actually didn't do what I wanted it to. How disappointing. How disappointing. It's probably coming from my out marker actually. What I may need to do, if I wanted to continue this, if I go position, this is some of the things that I would fine tune for me in the future for MATLAB. Just to do stuff like this, it will pick up on wiretaps like that. So you look there, it will pick up on wiretaps. That's just something for your notes, really, just for you to be aware of. But in the future, that's just something for you to score with. Now, the good thing is with this goes out to workspace, don't forget. If you're wanting to do the same here, the same system lies. If you're going to put to workspace, so let's go to workspace. Let's call this pos sim, because you can't have the same name popping out. So if I then tab you onto here, what we've got now is the same thing coming out. We can compare the two, we can look at the two, we can do all sorts with it, and even verify that it's actually giving us something a little bit more sensible. So what I'll do is bring you and you together, then go plots, and that did bugger all. Brilliant. But again, same thing lies. Go plot, and we got the same thing. Double M. This is getting very frustrating. And that is Simscape. And we come back. Where the hell have I put that? Oh, there it is. Now that is the first introduction to Simscape. What we will do is we will continue. I'd like to also show you how to solve the exact same thing in SolidWorks simulation, because a lot of people think you just hit motion and then that's it. It's actually not true. I wanted to smash some of them rumours, because these rumours are not true, 100% not true, and I wanted to just double check with them. So that is part B complete. Not as long as the last one, thank God, I hear you say. I hope you enjoyed this. I hope you found it insightful. We will continue on more and more information like this. We will continue on understanding of the system itself. Once we go that little bit deeper, I'm going to start dropping in new elements. So we're going to model a little bit of air resistance. We're going to model the coefficient of friction, and we're just going to spice it up, if you will. Some of these things will appear in the notes, in the sessions, the lessons. Some of these things will not. These are all just a benefit for you, and thank you for listening, and I will speak to you soon.